Welcome to today's custom-tailored deep dive.
Hey there.
You love staying ahead of the curve on artificial intelligence. So today we're just skipping the foundational basics entirely.
Yeah, we are diving straight into a massive bottleneck in the current development landscape.
Right. The fact that AI agents are phenomenal at writing code, but they are surprisingly terrible at actually finding bugs.
It is a really fascinating disconnect in the current generation of tools.
Definitely.
Today, we're looking closely at a groundbreaking 2025 paper by you and colleagues. It's titled OrcaLoca, an LLM agent framework for software issue localization.
OrcaLoca. I love the name.
Right, and this research isolates a specific pervasive limitation in how language models interact with large-scale environments.
Because the big picture problem here is that autonomous tool systems you're probably familiar with, like Devin or GitHub Copilot, they can effortlessly generate the syntax for effects.
Oh, absolutely, they can write the code.
But they struggle to find the scene of the crime, so to speak.
Exactly.
Localization. Pinpointing exactly where a specific logic error lives within a sprawling, interconnected codebase. It's notoriously difficult for them.
It really is.
So today, we're exploring how the OrcaLoca framework fundamentally solves this. It basically turns the AI into a highly methodical, structurally aware digital detective.
A very methodical detective.
Okay, let's unpack this.
To really appreciate what OrcaLoca achieves, we first have to quantify the environment these autonomous software engineering systems, or ASE systems, operate within.
The sheer scale of it.
Right. The researchers benchmark their framework using the SWE bench dataset.
And the size of the average code base in that dataset is wild.
It is. It contains roughly 3,010 files, which translates to about 438,000 lines of code.
Just imagine dropping a large language model into 438,000 lines of code.
With almost zero guidance.
Right, with just a vague, imprecise user complaint like, the generated database migration is missing an import statement.
It's a recipe for catastrophic failure.
You simply cannot stuff 500,000 lines of text into a context window.
No, you really can't.
Even with modern models that boast these massive context limits of 1 million tokens or more, you hit severe attention degradation.
The needle in the digital haystack problem.
Exactly. The model's attention mechanism gets diluted, and it completely loses the plot right in the middle of the prompt.
Which is precisely why, prior to OrcaLoca, models were just hitting a developmental wall. The paper notes a really striking statistic regarding this limitation.
Oh, the 53.5% wall.
Yes. Previous state-of-the-art AI agents only achieved a correct function match 53.5% of the time.
They were barely finding the right function half the time.
Barely better than a coin toss in some complex scenarios. By analyzing these failures, the researchers categorized the core issues into 3 specific AI traps that plague agentic systems.
Okay, let's break down those 3 traps.
Sure.
Trap number 1 is defined as inefficient action planning. The AI simply gets lost navigating the architecture of the repository.
Right. Previous agentic systems generally utilized one of 2 really flawed approaches.
What was the first one?
They either allowed the LLM to roam completely freely, which inevitably resulted in highly unstable, redundant search patterns.
Like it just keeps checking the same empty rooms over and over.
Exactly. Repeatedly requesting the exact same files. Or, conversely, they enforced rigid graph-based rules.
Which restricted the AI to only evaluating immediately neighboring nodes in the code structure.
Right, and that rigidity prevents the system from making the necessary intuitive jumps across a disparate code base.
Makes sense. So trap number 2 is the classic conciseness versus completeness trade-off.
The information retrieval paradox.
Yes. If you provide the AI with just the skeleton of the repository, only the class names and function signatures, it misses the granular execution logic where the bug actually hides.
It doesn't have enough detail.
But if you provide the complete unedited source files,
It drowns in irrelevant syntactic noise.
Exactly. Which leads directly into the third trap.
Context mismanagement.
Enterprise-scale repositories are messy.
So messy. They're filled with inherited classes, complex function overrides.
Identical variable names scattered across completely different modules.
Right. And as an AI searches through these files, the standard behavior is to sequentially concatenate everything it pulls into its active context window.
It just hoards data.
Yes, it accumulates a massive history of irrelevant, misleading information, which fundamentally muddies its reasoning capabilities.
It gets confused by its own notes.
Exactly. What's fascinating here is how OrcaLoca completely reimagines the approach to these three
It
traps.
doesn't just ask for a bigger model.
No. Instead of merely requesting a smarter underlying language model, it engineers a fundamentally superior work environment for the model it already has.
Tackling that first trap, the inefficient planning, brings us to OrcaLoca's first major innovation, priority-based scheduling for LLM-guided actions.
They essentially strip away the random walk nature of previous agents.
And they give the AI an action scheduler queue, the ASQ.
It operates as a highly structured, dynamic to-do list.
Like having a project manager looking over the AI's shoulder.
That's a great analogy. The ASQ operates with a built-in mechanism for dynamic urgency.
How does that work in practice?
Well, under normal conditions, an action the LLM proposes, like reading a file or searching a keyword, is assigned a baseline priority of level 1.
Standard priority.
Right. However, the framework actively monitors the agent's underlying intent.
Okay.
If the LLM repeatedly attempts to access a specific concept or structural area, let's say a serializer factory method, the queue's urgency counter ticks upward.
It notices the AI is really interested in that one thing.
Exactly. The system interprets this repeated intent as a signal of high relevance and automatically bumps the priority of that specific action to a level 3.
It fast-tracks it.
Yes, bypassing other standard tasks.
Wait, if the system automatically escalates the priority of a file just because the AI keeps looking at it, doesn't that introduce a massive risk?
A risk of what?
Of the AI getting hyperfixated on a dead end. We know LLMs are incredibly prone to hallucination loops. It seems like the agent could just continuously prioritize an irrelevant file until it exhausts its token limit.
That is a highly critical vulnerability in standard iterative architectures.
So how do they stop that?
It is exactly why the researchers paired the ASQ with a secondary layer called the Action Search Database.
An action search database.
Right. It acts as a strict structural memory. It prefetches unique identifiers, or UIDs, directly from the system's underlying code graph for every single action.
So it tracks the actual architectural identity of the code block, not just relying on the specific text string the AI typed into the search prompt.
Correct. Suppose the AI executes a broad search for a class called Model Choice Field.
Okay.
The database logs the specific UID for that class entity.
Got it.
Several steps later, the AI might gather additional context and decide it needs to explicitly search for Model Choice Field within the Django Forms models.py directory.
Even though it's technically the exact same class it already looked at.
Yes. In a traditional framework, the AI would execute that second search blindly.
Burning valuable token allocations and compute time to retrieve code it already possesses in its context history.
Exactly. But here, the Action Search Database intervenes.
It catches a duplicate.
It cross-references the UIDs, recognizes that both search queries map to the exact same architectural entity, and actively flags the new action as a duplicate.
That is brilliant.
It strips the duplicate from the queue before the LLM can expend resources or fall into a repetitive loop.
Here's where it gets really interesting. Preventing execution loops handles the navigation aspect. But eventually, the AI is going to locate a massive, highly complex file that it genuinely needs to parse.
And that brings us to their solution for the second trap.
The conciseness versus completeness trade-off.
Right.
To solve this, OrcaLoca deploys a multi-agent workflow referred to as action decomposition with relevance scoring.
Rather than dumping a 5,000-line class directly into the primary LLM's context window.
Which we established causes attention degradation.
Right. OrcaLoca delegates the cognitive load. It takes a high-level, bulky action such as investigate this large monolithic file and systematically breaks it down.
It slices it up.
Those granular sub-actions are handed over to a secondary independent sub-agent evaluator.
The sub-agent functions somewhat like a dedicated paralegal for a lead attorney.
I love that comparison.
Its sole operational purpose is to scan through that massive file in isolation, and it assigns a mathematical relevance score to every single method inside it, benchmarking them against the semantics of the original bug report.
It handles the heavy lifting of reading the fine print, so the primary reasoning agent remains completely unburdened.
So it's not just summarizing, it's actually scoring.
Yes. And the subagent operates under a highly strict top K constraint to enforce conciseness.
A cupcake rule.
Based on the optimal configuration detailed in the paper, the subagent is restricted to returning only the top 3 most relevant methods for any given class.
Just the top 3.
Or the top 2 structural elements for an entire file.
It aggressively filters the syntactic noise before it ever reaches the main reasoning loop.
Those top-scoring decomposed segments are then assigned a level 2 priority and fed directly back into the primary agent's action scheduler queue.
So the lead LLM only ever processes the most highly concentrated, structurally relevant snippets of logic.
Exactly.
And that decomposition process completely alters how the system manages structural ambiguities too.
Oh, namespace collisions.
Right. In a mature code base, you frequently encounter namespace collisions. You might have a MySQL implementation of a SQL compiler class residing in one directory.
And a PostgreSQL implementation of that identical class name in another directory.
Exactly. If the primary agent requests SQL compiler, a naive information retrieval system typically grabs the first match it indexes.
Which severely derails the investigation if it happens to be the wrong database protocol.
So how does OrcaLoca handle that?
It utilizes an inverted index specifically to catch those exact namespace ambiguities. When multiple UIDs match a single generalized search query, the system forcibly pauses the execution flow.
It stops and asks for directions.
Basically, yes. It presents the ambiguous options back to the primary AI, effectively forcing the model to generate fine-grained, decomposed actions to investigate each specific architectural path independently.
It systematically dismantles the ambiguity rather than relying on probabilistic guessing.
Yes, which establishes the foundation for solving the third trap, context mismanagement.
Because even if the subagent is feeding the primary LLM highly concentrated relevant snippets,
those snippets cumulatively add up.
right. If the model retains every single decomposed method in its context window indefinitely, it will inevitably suffer from the same attention degradation and hallucination issues.
The workspace needs strict boundaries, keeping the desk clean, so to speak.
To maintain an unpolluted context window, OrcaLoca relies on its context manager, which continuously performs distance-aware search context pruning.
And to grasp the mechanics of this pruning, we really need to examine how the framework mathematically represents the software.
It doesn't just treat the repository as a flat collection of text files, does it?
Not at all. It parses the entire application into abstract syntax trees, or ASTs, and constructs a comprehensive code graph.
It builds a three-dimensional dependency graph of the software's execution logic.
Yes, it maps out containment edges to structurally track which methods belong to which parent classes.
Who lives inside what?
Exactly. And it plots reference edges to monitor which functions actively call other functions.
Who's talking to who?
Right. With that graph topology established, the context manager applies a rigorous mathematical filter to the LLM's memory.
The distance-aware part.
Every time a newly searched piece of code is pulled into the active context, the system calculates the average shortest path distance across the code graph.
It measures the exact structural distance between that new code snippet and the currently suspected bug locations.
It is essentially running a breadth-first search calculation on the dependency graph.
So if the AI pulls a utility function that is 10 reference edges away from where the application is crashing,
it is mathematically deemed less relevant than a function that directly invokes the crashed method.
makes total sense.
Based on that computed topological distance, the context manager ruthlessly prunes the context window.
It just cuts it off.
It ranks the items and strictly retains only the top 12 most structurally relevant entries.
Just 12.
Older, less connected searches are immediately purged from the active prompt.
The AI is continuously forced to focus solely on the immediate syntactic neighborhood of the problem.
Completely eliminating the irrelevant history that derails standard models.
I want to pivot slightly to a methodological detail from the appendices that fundamentally rounds out this approach.
The reproducer agent?
Yes. We spent significant time discussing how the system navigates the code graphs. But how does the AI actually know what the bug looks like in practice?
Right, because a vague user issue report, like the UI is rendering incorrectly, isn't always enough semantic data to initiate a graph search.
Yep. Exactly. OrcaLoca includes an auxiliary reproducer agent to bridge this gap.
The reproducer agent is engineered to provide empirical grounding.
It actually tests the code.
It is tasked with taking the potentially buggy repository, spinning up a fully isolated Docker container, and attempting to trigger the failure dynamically based on the issue description.
When it successfully induces the crash, It utilizes a Python tracing utility called VizTracer to capture the exact execution flow of the application.
But it doesn't just dump the entire raw stack trace into the AI's prompt.
No, the paper specifies that it extracts specifically the top 25 actual stack trace errors.
Right.
Why strictly limit it to 25? If you have the complete telemetry of the crash, wouldn't more data be better for the LLM?
That limitation ties directly back to managing the conciseness versus completeness trade-off.
Oh, of course.
Execution stack traces in layered enterprise software can easily span thousands of lines. They get bloated with framework boilerplate, middleware operations, and library calls that have absolutely nothing to do with the developer's specific logic error.
It's the wall of text.
By hard filtering the VizTracer output to the top 25 most recent functional invocations leading up to the exception, the reproducer agent isolates the exact microsecond the logic failed.
Feeding that highly targeted empirical trace to the main search agent acts as a massive heuristic shortcut.
It provides the localization process with a highly accurate starting coordinate directly on the code graph.
Let's transition to the scoreboard and analyze how this intricate architecture translates to actual measurable performance.
The numbers are really impressive.
The research team benchmarked OrcaLoca against 17 different state-of-the-art systems utilizing the SWE Bench Lite dataset.
And the performance improvements are highly substantial.
Earlier, we noted the 53.5% baseline average for correct function matching among previous models.
Right. OrcaLoca achieved a 65.33% function match rate,
That's a huge leap.
alongside an 83.33% file match rate. It is navigating hundreds of thousands of lines of complex logic with a degree of precision we have simply not observed in open-source frameworks.
It actually managed to uniquely localize 6 highly complex issues that heavily funded massive agentic frameworks like OpenHands or AutoCode Rover completely failed to map.
Furthermore, localization is ultimately only half the battle. The terminal goal of ASE systems is autonomous resolution.
Actually fixing the bug.
Yes. To test this, the research team paired OrcaLoca's localization outputs with the code editing capabilities of an existing framework known as Agentless 1.5.
And what happened?
That integration resulted in a 41% final issue resolved rate.
Wow.
That represents a 6.33 percentage point improvement over running the Agentless 1.5 system in isolation.
Pinpointing the exact structural location of the bug fundamentally improves the downstream AI's ability to synthesize the correct patch.
It really does.
And we should address the unit economics of this system. Deploying complex multi-agent architectures can rapidly deplete API budgets due to high token overhead.
Absolutely.
But because OrcaLoca is so incredibly strict regarding context pruning and blocking redundant searches via the database, it remains highly cost-effective.
Very cost-effective.
Running on the Claude 3.5 Sonnet model, a full localization search costs approximately 87 cents per issue instance.
And the researchers actually optimized the operational costs even further.
Oh, right, the batch actions.
They implemented a feature called batch action execution, which permits the primary agent to process groups of top priority actions simultaneously rather than in a strict sequential loop.
Which saves trips to the API.
Exactly. That specific architectural tweak reduced the token overhead by 34%, driving the localization cost down to just 58 cents per issue, with absolutely no degradation in diagnostic accuracy.
58 cents to algorithmically pinpoint a bug within a 500,000-line enterprise repository? That is unbelievable.
It's a game changer. And to validate that these performance gains were actually derived from the OrcaLoca framework itself and not merely relying on the raw reasoning power of the underlying Claude model, the team ran extensive ablation studies.
Taking away parts of the system to see what breaks.
The ablation studies are arguably the most telling component of the entire paper. They systematically disabled individual modules of the framework to measure the resulting degradation.
What did they find?
Removing the priority-based scheduling caused a measurable drop in navigational efficiency.
So the queue matters.
Disabling the sub-agent action decomposition lowered the overall match rates as the model became overwhelmed by file size.
The paralegal matters.
And turning off the distance-aware searched context pruning resulted in a severe 3 to 5 percentage point penalty across the board.
Every single piece of the puzzle is vital.
Every single distinct architectural choice is mathematically necessary to achieve that 41% final resolve rate. If we connect this to the bigger picture, these results represent a necessary paradigm shift in how the industry approaches agentic AI.
We can't just keep scaling up.
The prevailing developmental trend has been to simply train larger models with continuously expanding context windows, relying on the model to eventually sort through the noise.
Brute force.
OrcaLoca proves that providing structured algorithmic guardrails like semantic dependency graphs and rigid mathematical memory pruning is a fundamentally more efficient and accurate methodology for solving complex spatial reasoning tasks.
So what does this all mean? If you are listening today, whether you write code, manage a technical engineering team, architect software solutions, or just closely track the evolution of artificial intelligence, OrcaLoca provides a highly clear blueprint.
A very clear one.
The future of AI isn't solely about scaling up the parameters of a single massive neural network. It's about designing significantly smarter external systems surrounding those networks.
Working smarter, not harder.
Exactly. It's about utilizing specialized subagents to process the dense reading, enforcing strict mathematical boundaries on what the model is permitted to retain in memory, and transforming unstructured textual data into traversable architectural graphs. It is the ultimate demonstration of engineering smarter workflows rather than just throwing more compute at the problem.
I will leave you with an extrapolation of that exact concept. We have spent this time analyzing how OrcaLoca grants a language model the requisite spatial awareness to successfully navigate 400,000 lines of interdependent software logic.
Right.
Consider what happens when we abstract this specific architectural framework and apply it to other massive, complex data sets.
Oh, outside of software.
Imagine deploying an OrcaLoca-style agent to navigate a hospital network's decades of interconnected medical records, utilizing a graph to isolate the root cause of a patient's rare cascading condition.
That would be incredible.
Or imagine mapping out a century of legal archives into a dependency graph, utilizing a specialized sub-agent to locate a single winning precedent buried within millions of pages of complex case law.
The localization problem is everywhere.
The localization problem is a universal bottleneck across countless domains, and this graph-based, tightly pruned framework might just be the structural key to solving it across the board.
A phenomenal concept to end on. The potential applications really are practically limitless once you provide the AI with a proper structural map to guide its reasoning. Thank you for joining us on this deep dive today. We hope this provided a clear, rigorous look into the cutting-edge methodologies of generative AI frameworks. Keep questioning the architectures around you, keep exploring these frontiers of knowledge, and we will catch you on the next one.